So we've talked about what happens with the aircraft in several different phases of flight. But today, let's talk about what happens during a turn. And in particular, what we're going to talk about is the steady, coordinated turn. Okay, so steady, meaning that we are not accelerating in the direction of flight, and coordinated in that coordinated means that the apparent gravity is out the bottom of the airplane. And so we'll talk a little bit more about that in just a minute. Okay, but first, I wanted to point some things out. Okay, so first we're going to draw the aircraft in its steady coordinated turn, and I've pre-drawn these drawings because they're a little bit difficult to do in a digital format. But what we have here is a front view of the aircraft. That's this one here, so this is front. We have a side view, and then we have a top view as well here at the bottom. Okay, so let's put the forces on these different views. Okay, so on our front view, that's the one here at the top left. Well, the first thing that we can put in here is the weight acting down. And then we also have the lift. Now the lift is going to act out the top of the aircraft, okay, because that's the direction that the lift acts based on the lifting surfaces on the aircraft. Now the angle between the lift and the vertical is what's known as the bank angle, and that's this angle right here, and we're going to call that phi. Okay, phi is the bank angle. I'm going to label the lift here, and this is the weight. Okay, now let's go to our side view for just a second. We'll come back to the front view because there's something that we're missing, and you may have already picked up on this, but we'll come back to it. So on the side view, the first thing we'll assume is that the thrust acts aligned with the aircraft's direction of flight. So in other words, there is no thrust angle. And the drag, of course, would act opposite that, parallel to the direction of flight. And the lift is going to act perpendicular to the direction of flight. And then our weight will act straight down. Okay, now this is kind of a crazy orientation here because we're at a bank angle, and we have front, side, and top views. And the forces that I'm drawing here are projections of the actual forces. The actual forces are acting in three-dimensional space here. When I'm drawing our projections of those forces in the respective plane, okay? So in that case, we have a couple of things going on. So the first thing is that this lift is actually a projection of this lift in the vertical plane. Okay, so the lift in the front view projected onto the vertical plane. So that makes this L cos gamma, or L cos phi, excuse me. Thrust is just thrust, drag is just drag, and weight here is just weight. Okay, now this angle we know as the climb angle, or gamma. Okay, now as I said, we were going to come back to the front view. The front view that we have here is actually what we would get if we had a camera. Pretend this is a camera. It looks a little bit more like a milk jug, but a camera looking straight down onto the nose of the aircraft. So this weight actually is a projection of the weight, like something like this, where this angle is also gamma. So really what we have here on the front view is W cos gamma. I hope that makes sense. It's a little bit confusing because we're doing projections of things onto planes, but I just want to be really clear about it. Okay, now on this bottom thing here, which is the top view, there's a couple things to label. First is R, which is the radius of the turn. Okay, and just to be clear, that is this right here on the front view. And then here we have our velocity, but this is our velocity. This is v cos gamma, right? Because our velocity acts at this angle here. I'm going to just draw that right there. So that's our velocity, and so a projection of that onto the top plane would be v cos gamma. Okay. Now the force, we're only going to label one force on this, and that there's a component of the lift that acts inward toward the center of the circle, and that is going to be L sine gamma, right? Because that, of course, is then the projection. It's something that falls right here. Or, excuse me, I keep saying gamma. L sine phi, sine of the bank angle. So that corresponds to this lift here. Okay, so I hope all that makes sense. So we can take this kind of funny free body diagram and pull some forces off it. So first, what we're going to do is we're going to look at the forces. So the forces in the radial direction. Okay, so the forces in the radial direction. Let me just underline this real quick. Here we go. Well, the way we can find these is first there's one thing that we need to recall. Okay, so when we are in a turn like this, there's a radial acceleration. And the so recall radial acceleration, which we're going to call this A sub r, is just the transverse velocity divided by r. Transverse velocity squared divided by r, pardon me. Now the transverse velocity we have, it's v cos gamma. So when we balance the force, we'll be able to figure out what this is. So let's balance the forces here. So we have a force acting inward, and that's L sine of phi. Okay. Now the radial acceleration, well, and this equals mass times our radial acceleration, because our radial acceleration actually acts outward this way. And like we said, it's Vt squared over r, where Vt is actually v cos theta. So really we have L sine phi equals v cos phi. Man, I'm having trouble with my angles. V cos gamma, I think I said theta earlier too. Excuse me. V cos gamma, here we go, squared divided by r. Times, and now mass is just the weight divided by gravity. And we do it this way because we know that weight shows up on our forces here. Okay, so let's remember this equation. Okay, we're going to call this one star. Okay, now let's sum the forces in the direction of flight. So direction of flight. And if you'll bear with me, I'll underline this one as well. Okay, so in the direction of flight, we have the thrust and the drag. And then we also have a component coming from the weight. Okay, so let's just put those together. So we have the thrust, and that's going to equal the drag plus W sine of gamma. Okay, and of course we know that the drag, sorry, this is a plus sign. We know that the drag is a function of the lift coefficient, so we're going to rewrite this as T equals 1/2 rho v squared SW times CD naught plus CD naught L times CL plus CD CL squared, pardon me, CL squared over pi E RA plus W sine of gamma. Okay, now let's remember this as well. We're going to call this double star. And then finally, we need to sum the forces in the direction that is orthogonal to both the radial direction and the direction of flight. Okay, so the radial direction is in toward the center of the circle. The direction of flight is inclined at an angle gamma. And so the force normal to this one is going to be the vertical but inclined back gamma, if that makes sense. So I'm just going to call this, I guess, the other direction. It's a great name, I know. But in order to make this completely, a three-dimensional analysis here, we've got to have this other direction that's normal to the other two. Okay, and this one, if we sum the forces in this, we're going to have L cosine of phi, right, because that's aligned with the vertical. This direction is what we're looking at down on the front view. So L cosine phi, and that's going to equal W cosine of gamma. Now, we can simplify this to come out to be lift equals W cos gamma divided by cosine phi. And of course, we can then transform this to the lift coefficient, which is going to be W cos gamma divided by 1/2 rho v squared SW, it's a 2 by the way, times cosine of phi. Okay, so let's remember this as well. We're going to call this triple star. Okay, so from these different equations that we have, star, double star, and triple star, such unique names, we can come up with a couple of things. The first thing that we want to know is what's the radius? How do we decide what the radius of the turn is based on our aircraft operating parameters and design parameters? So I'm going to do this in green. So the question is, I'm going to find the turn radius. And of course this is R. So the way that we do this is actually pretty simple, because we have equations that have R in them. So let's go back up to this first one, star. So here we have R, and then we also have phi, W over G. These things are all just kind of things that we know, but L we have an equation for. So why don't we sub in triple star into star? So let me write it down here. Sub star, triple star, excuse me, into star. So if we do that, I'm going to try and keep both these equations on here at the same time. What we get is we get W cos theta, cos gamma, excuse me, times tangent of phi, right? Because tangent is the sine of phi divided by the cosine of phi. So tangent of phi equals W over G times V cos gamma squared divided by R. So we can see that the W's cancel, one of the cosine gammas cancels, and we can simplify this to give tangent of phi equals V squared cos, wow, sorry about that smudge, V squared cos gamma divided by GR. And then if we solve this for R, So solve for r comes out to be that r equals v squared cos gamma divided by g tan phi. Great, so there we have it. There's our turning radius. Okay, so what else might we want to know? Well, it might be interesting for us to find out what gamma is, right? We want to know what the climb angle is based on our different parameters like our thrust, lift, drag, things like that. So let's look at that. So I'm going to be jumping back and forth, and I apologize for that. I'm just kind of trying to deal with the space I have here. Let's do this in red. So climb angle gamma. All right, so the climb angle, the way that we find this is we're going to come back up and we're going to look for equations that have the climb angle. Well, they all three have it, but let's take the drag, okay? Because we have this sine of gamma, and we know that if we use a small angle approximation, then that can be simplified to be gamma. Okay, so let's just use this, okay? So if we're going to use this to find gamma, well, there's a few things in here. One is we have the CL, okay? Well, we know what the CL is, again, from triple star. So why don't we sub triple star into double star? So we're going to sub triple star into double star. Okay, and when we do that, let's go back up just for a second. That lift coefficient goes in to our expression for the drag. So let's go down a little bit here. What we end up getting is this. T equals 1/2 rho v squared SW times CD naught plus CD naught L times W cosine gamma divided by 1/2 rho v squared SW cosine phi plus all of that again, so W cos gamma divided by 1/2 rho v squared SW cosine phi squared divided by pi e RA. All of that plus W sine gamma. Now we can simplify this by multiplying through our 1/2 rho v squared SW, and what that gives us then is T equals 1/2 rho v squared SW CD naught plus CD naught L W cos gamma divided by cos phi plus, and here I'm going to simplify a little, 1 divided by 1/2 rho v squared SW times pi e RA all times W cos gamma divided by cos phi squared all plus W sine gamma. Okay, and then from here we have a nice expression that we can solve to get sine of gamma. And here we're going to solve for sine of gamma instead of gamma explicitly. So we get T minus 1/2 rho v squared SW CD naught plus CD naught L W cos gamma or cos phi plus all this again, 1 divided by 1/2 rho v squared SW pi e RA all times W cos gamma divided by cos phi squared all divided by SW, and I am not even going to attempt to freehand this line. I'm just going to cheat. All divided by W. And there you have it. Okay, so there's an expression that we can use to get the climb angle. Let's see if I can draw this line through here. Okay, then we're going to look at one more thing, and I apologize, I'm kind of going through this slow so that we can really, pick this out, and they're kind of long, hairy equations. Okay, so the last thing is to get the climb rate. But if you'll recall, the climb rate, which I'll do in yellow, climb rate VC, the climb rate is just V times the climb angle. So VC equals, the sine of the climb angle. So V sine gamma. And so if we do that, then all we have to do is just multiply what we have here by V. So we find that VC equals, and I'm going to substitute TV for power available, because that's our thrust available times the velocity, minus 1/2 rho V cubed SW CD naught plus CD naught L times VW cos gamma divided by cos phi plus 2 over pi ERA rho V squared SW times W cos gamma over cos phi, squared, all divided by W, which again, not even going to attempt to freehand, all divided by W. Okay, and there's our expression for the climb angle. Now, we can make a common assumption, which is that the climb angle is small, and basically we just get rid of this cosine gamma. Okay, so I'm not going to go through that here. That's a straightforward thing to do. But the thing I wanted to point out is when we do that, then this bracketed term here becomes our power required. If gamma is close to 0. Okay, so just one last thing to note. If we have more power available than this bracketed term, the power required, then we will climb when we are in our turn. Now, if we have, well, what you'll notice here is that this is a greater quantity than the power required in steady level flight. Okay, and so because of that, I think I forgot a bracket here. So because of that, when we go into a turn, the pilot has to increase throttle. So any of you pilots out there, you'd know this, right? When you go into a turn, you increase the throttle to stay at the same altitude so you don't start sinking. Because if you stay at the same throttle setting, then your power required will increase, but your power available will not, and so you'll start to sink. Okay? So I think I said something backward before. Of course, if your power available is greater than the bracketed term, you'll climb. If the bracketed term is greater than your power available, you'll sink. So anyway, those are just, so just to review, this was kind of a longer segment here. We derived the turn radius, the climb angle, and the climb rate from a free body diagram of a coordinated turn, steady coordinated turn. And so we're gonna build on this as we go forward. So I encourage you to be really solid on this.